Implicit differentiation. This is one of the coolest techniques ever in Calculus 1, just because it allows you to skip a lot of boring calculations, especially when it comes to finding y as a function of x. And that's the big takeaway here. Whenever you see an expression, say this, right? Y is a function of x, so you could write it as, here's what you could do, right? You could do y squared equal 25 minus x squared, and then taking the square root. That's the first problem you find right there, because you have two possible solutions, and if you want to derive, you have to derive both, so that's already an issue. But even then, you have an ugly square root. If you've seen it before, we've done it with the chain rule. This 1/2 comes down. It's kind of annoying. And if you have more complicated situations, look at this. Even solving this for y is already an issue, right? It's already difficult to do. We can't do the same that I just did for 1 with equation 2. So on equation 1, it is possible to solve for y, but solving for y just makes it more difficult than it would be to find the derivative if I didn't solve for y using implicit differentiation, which is what we're going to talk about now. These two, for example, you can use the chain rule easily. This one here, you can use the product rule easily. But for the other two, it's kind of an issue, right? If you don't have y equals some function of x. So what do? You simply pretend like you have two different functions. So the idea is we act as though, and I write it as the idea, you act as though x squared plus y squared equal 25 is actually giving you two functions on the left side of function f of x, and on the right side a g of x, where f of x equal to x squared plus y squared and g of x equal to 25. So you actually have two functions in there. And the one thing you have to remember is that y is already a function of x. So f of x is really x squared plus y of x squared. So you now have two functions, and the equation is telling me that f equals g. So it has to be that the derivative of x equals the derivative of g. So I'm saying if f equals g, then their derivatives are also equal. Okay, that's the idea. And then here you're going to see the two alternatives, how you do that if you didn't use the chain rule, right? If you remember, this is the equation of a circle, and the two alternatives that I gave you are actually the two different halves of the circle, one positive, one negative, one above the x-axis, one under. And then if you were to derive, you'd have to derive both and then decide which one to use. It's just a lot more work. And the other equation, this one is called the folium of Descartes, the famous French mathematician that came up with the idea of the xy plane, right? Of the rectangular coordinate system. It's just another example of where you could use it. So let's go ahead and start talking about how to actually use it. Here they're just explaining the same idea I showed you, right? You're calling this little thing f of x, and then you're deriving both sides with respect to x, right? That's what you're doing, which is what I just told you about. Yeah. So let's go ahead and go on to how we can use this, and this is why it's called implicit differentiation, because we're not really writing the function, the two functions on both sides. We're just implicitly thinking of it that way, right? And then we're using this idea. That's why implicit differentiation. We're not really writing the function little f and little g that I talked to you about at the beginning. So let's see how we'd actually apply this. So we have x squared plus y squared equal 25. So this one time I'm going to rewrite this as x squared plus y of x squared equals 25. This one time I'm going to do that. but I'm not going to do that again. But whenever you feel like you see that I'm using implicit differentiation, you should think about it that way. A good hint to see that I should use implicit differentiation is what they're asking me for. They're asking me for dy dx, which gives me already that y is a function of x, right? Otherwise, it wouldn't make sense to derive y in terms of x. Okay, so now I derive both sides, which is what we were talking about before. So I'll go ahead and add this in red. And then I'll keep solving this. Okay, so the derivative of x squared is true x with respect to x. The derivative of this, I gotta use the chain rule. Okay, so I go 2 y of x times y prime of x. Yeah? Stop for a second. Think about the chain rule. Because the chain rule was the previous section, I'll sort of true it up for you. I'll tell you exactly how this goes. We can say, right, that, let's see, we can say u equals y, and then f of x equals x squared, or f of u I can say, right? Let's say it again. F of u equals u squared, u equals y of x, right? So df dx is df du, which is this, right? It's 2u, right? Times du dx, which is just the derivative of y, which is this. So this is the chain rule on the left-hand side, but then we still have to derive the right-hand side, which is the derivative of 25, which very luckily equals 0 for us, right? So we end up with this Boole equation there. Remember what we're looking for, right? We're looking for dy dx, so we're looking to solve for this. So I'm going to go and do 2x plus 2y of x, y prime of x equals 0. Zoom out a little bit more. And then, okay, I want to solve for this. So I'm subtract 2x. Can cancel the 2's. And then y prime of x equal to minus x over y of x. Okay. Isn't that awesome? Even though I don't know what y of x is, I haven't solved for it. I have a clean expression for y prime of x that only depends on x and on y. Let me rewrite this because it's looking very wonky. Okay. Look at B. Find the equation of the tangent to the circle at the point 3, 4. So note that they're not just giving us x, they're giving us x and y equals 4, x equals 3 and y equals 4. So they're giving us both coordinates, because if you look at the right hand side of the result of the implicit differentiation, you have both x and y. Yeah. So if I start working on it, I'll see y prime of x, split it in two parts again. Y prime of x equal to minus, I'm actually looking for x equals 3, right? So y prime of 3 is minus 3 over y of 3. So that's minus 3. Y of 3 equals to 4. That's what was given to me. So that's minus 3/4. That's the slope of the tangent line. So I quickly found the slope of the tangent line. Now I'll work on the actual equation. So the point slope equation x minus, start with y, right? Y minus y is 0 equals m times x minus x0, so y minus 4 equals minus 3/4 x minus 3. You can leave it that way if you'd like, or you can use distributive property and add the 4 to the right side to get the slope-intercept. That's usually my favorite form, but I'll stop here because you know what to do from here. In the end, we were able to find the slope of the tangent line. We were able to find the slope of the tangent line without large issues, without having to deal with at least square roots, which was the alternative back at the beginning, right? Handling this square root right here. So let's go back, and now you understand why it's useful and important. You see the other solution, because the other solution would be to actually do this. So I'm not going to do it, but I'll let you follow along on the books or the slideshow's solution here. You see that it's actually going to work the same way, right? And you can see the equation of the tangent given here. Let's talk a little bit more now about how we can use these two rules, or these two techniques we just learned, first the chain rule and the implicit differentiation, to find the derivatives of the inverse trig functions, which I think are the last functions we're going to learn how to derive for now. Remember that we're dealing with inverse trig functions, so we're dealing with sine inverse of x. Sometimes it's called the arc sine of x. My favorite way to write this, just to avoid confusion with the -1, is to write y equals the arc sine of x. But whenever I write this, remember that I'm saying y equals arc sine of x. Y is the angle whose sine equals x. Okay? So x is a value, y is an angle. So just as a reminder, y equals the arc sine of x. So let's say, what's y of 1/2? So that will be an angle whose sine equals 1/2. So arc sine 1/2. So an angle that I know whose sine equals 1/2 is 30 degrees, so pi over 6. So I always give it in radians, and I always have to remember for arc sine, at least, that the domain, or the range rather, the angles have to lie between pi over 2 and negative pi over 2. So the right half of the circle, of the unit circle. So I always have to be here, between minus pi over 2 and pi over 2, at least for arc sine, okay, for the inverse sine. Okay, whatever. Why am I saying all this? Because, well, if I start with this, and remember in Math 142, if you took Math 142 with me, that's how we dealt with this. Whenever I had an equation like y equals the arc sine of 1/2, or the sine inverse of 1/2, that's the same as saying that y is an angle and the sine of y is 1/2, right? Just do the same with x this time around, right? Okay? So you have this equation, sine of y, remember what we did before with implicit differentiation, sine of y of x, right, equals x, right? So now I can use implicit differentiation and derive both sides. So I do d dx of that equals d dx of x, right? Too many parentheses, so I'll change one of the parentheses to brackets. And now I gotta use the chain rule. So let's see if you're good with that. So I gotta go d dx of sine. The derivative of sine is cosine, so cosine of y of x times the derivative of y of x, so y prime of x, and that's the gold right here. That's what I'm looking for, right? Because that's the derivative of y, right, of the arc sine. And that equal to the derivative of the right-hand side, which is 1. Yeah. So the derivative of this is this. The derivative of this is this. Okay? Okay, I want to find that though. So that's going to give me y prime of x equals 1 over the cosine of y, of my angle. Remember that. So I got to find the cosine of that angle. So how do I deal with this? I can go and say, let's see if I do this on this page. On the next one. Okay, so far I have this. So now I want to go and find the cosine of y in terms of x only. So remember that the sine of y equal to x. So if I draw a triangle, a right triangle, I call this the angle y, right? The sine equals x will be, remember that the sine equals the opposite over the hypotenuse, and that's x over 1, right? That's just x. So I can say that the opposite's x and the hypotenuse is 1. And that bottom here is unknown to me, right? So I can call it some letter, I don't know, z. So z squared by Pythagorean theorem plus x squared equal to 1, right? So z is the square root of 1 minus x squared, right? The cosine is positive because x is in that quadrant there. So that way, the cosine of y, remember I'll redraw the triangle here. This is y, it's 90x1 square root of 1 minus x squared, right? Just found it. So the cosine of y is the adjacent over the hypotenuse, which is just 1. So y prime, which is what I was looking for, remember it was 1 over cosine of y. It will be 1 over that thing I just found. It's 1 over 1 minus x squared. Okay, I'll erase this one here because you don't need it. And that's the derivative of the arc sine. Okay, so I'll write in red and I'll box it. The derivative of sine inverse of x, that equal to 1 over square root of 1 minus x squared. Very, very important. And like I said, like I always say when it comes to memorization, either you remember this or you got to be able to do this process, you know, this whole process here on this page. Up to you. Okay? Either one works. But I guess in a Calculus 1 course, it's a good idea to have at least the more basic ones, like sine and cosine, memorized. You can do the same with secant, or something similar with secant, right? They're actually just finishing it. But what I'm saying is you can do the same to find the tangent inverse. That's another one that either it's good to memorize. It's not that hard to memorize, but either you memorize it or you find it. And this is a cool little example of us using many of the rules. So we're not going to use just the one rule. So we're going to use more rules today. So let's go with that. So we're going to use the chain rule on that one. So y equals, I'll rewrite sine inverse as arc sine again because I just like it better. And it confuses me less when it comes to deriving things. And now I can say y equals arc sine of x to the minus 1, right? So now I can go and say dy dx that will be, so first the power rule, the minus 1 comes out, so minus 1 times arc sine of x, and I subtract 1 from the minus 1, becomes a minus 2, times the derivative of the inside from the chain rule, right? So that will be minus arc sine squared x. I'll just keep it like this, because this is a negative, right? So it can go down onto the fraction. So minus 1 over sine x squared times the derivative of arc sine is what I just found. So it's the square root 1 over the square root 1 minus x squared. So it will be minus 1 over that whole thing, right? So I can write the whole thing together on the same denominator. So I'll just do it here. Wonder if it fits. Not using my space very well, so let me go and do that here. So dy dx equal to minus 1 over arc sine x squared times the square root of 1 minus x squared. Okay? Not looking great because of the space management, but that's the solution, right? For A. Just had to use the chain rule, not write it here. Before, and then I applied the derivative of the arc sine. Okay, so let's go again. Let's go B now. Here, B. So split this up into two parts. Y equals x arctangent of root x. Now they already wrote arctangent. They didn't use tangent inverse. And now I start with the product rule. So it's dx times arctangent x plus x dx arctangent of the square root of x. So we're in trouble now. This is easy. This is 1 times the arctangent x. This is easy. One reason why people don't like to write arctangent, they prefer to write tangent to the negative 1, is because it diminishes the amount of writing you gotta do. But for me, you know, it's more important that you don't get confused than that you write less. So I prefer to write more if it's to have more clarity. Okay, so now that we have it, we have x times, so first we got to find the derivative of arctangent, and we took that from before, dx of arctangent x, right? Note the difference. Note the difference. It's not of root x, it's just of x, is 1 over 1 plus x squared. So now, because we're using the chain rule this time, I have to apply square root of x to this. So it's 1 over 1 plus the square root of x squared from the chain rule times the derivative of the inside, which is root x, right? So I'm using the chain rule. Take a second to understand what I did. Pause this if you need. Look back at chain rule if you need. Just make sure that you look at it and you understand that I used the chain rule and which functions I chose for it. Okay? Alright. So this will be 1 times the arctangent is just the arctangent. And now the derivative of, so let me write this one first. It's 1 over 1. So the square root of x times, or the square root of x squared could possibly not be x, but because x is positive, just because we're taking the square root of it, it's going to be x. So I'm saying that square root of x squared equals x. Just remember that sometimes if you do the opposite, that may not necessarily be equal x. Okay, if you square it first and then you take the square root, you may not necessarily get that. You may get an absolute value. Okay, just remember that. But this order that we have is okay. Alright, but then the derivative of x to the 1/2, right? So d dx of root x is d dx of x to the 1/2. So by the power rule, that's 1/2 x to the minus 1/2. Right? Subtract, bring the 1/2 down and subtract 1 from the exponent. You get 1/2 x to the minus 1/2. So we're basically done. I just want to finish writing it well. So I'll write arctan x plus, okay, so we have x on the top and 2 square root of x times 1 plus x at the bottom, and that will be our answer. Okay, so here we use the product rule, the chain rule, and the power rule, all of them together, and that's how most of our calculus class is going to go from now on. You're going to use many rules in succession, one after the other. Okay, so you got to be very proficient with them. So go back, stop, watch these two problems again, A and B. I think they're very useful. And come to class, ask questions, so you're able to solve all of these as they come on. So this is a table of all derivatives of inverse functions. Like I said before, either you memorize them, and if I were to memorize, I'd memorize only these three. Okay, if I were to memorize, I'd memorize only these three. They're not that hard to memorize, but still, it takes brain power to memorize them. Maybe you don't want to do that. The alternative, and that's what I do, is you got to be able to do the process that we did on this page right here to find the sine inverse. We can do that in class again. If you have questions, you can ask and I can go through it again. But you have these two alternatives. Either memorize these three at least, or you got to be able to do the whole process again. These other three I'm not going to require you to know. If I put one of these in a problem, I either expect you to use the whole process and find what it is, or I'll just give you what the derivative of cosecant to secant to cotangent are. Okay. So that's it for this video. Good luck, study. Don't worry if you're having trouble, just keep working and you're going to get there.